So in the previous two parts, we basically figure out this expression for the variance if the data is projected onto one direction, say UK. So suppose we have data points like this, and we projected them onto one direction, say UK, which means we project these points like this, and these will be our new points in that direction, and we find the variance of these points in that direction, and it turns out to be this. And what we are doing here is basically we want to rotate this UK, basically going in another direction, say another UK prime, and we do the same thing, project all the data points onto this direction and compute the variance in that direction. And we want to compare which direction should we project these points to so that we maximize the variance. So by definition, that direction is called the principal component direction. So, so the one with the largest one is principal component 1, second largest orthogonal one is principal component 2, and so on. So the problem becomes we want to maximize this variance. Again, we derive this as the variance if it's projected onto that direction, and we are finding a direction that maximizes this, and we need a constraint such that these things are unit vectors. So unit vector means the norm or the length of this vector is 1, and square is also 1. So that's why norm squared is just UK transpose UK, which is this expression here. So we are going to use a technique called Lagrange multiplier. You do not need to know this for the final example. I'll briefly explain it. So the idea is you are maximizing a function subject to the constraint that another function is equal to not 1, 0. So what we're going to say is this maximization is actually equivalent to maximizing another expression f minus lambda g. And lambda is basically a huge cost. So we can change lambda, so we can make lambda huge. So what happens is that if this constraint is not satisfied, basically if g is not 0, lambda can be very, very large, and we're maximizing this, so it means we're getting subtracted a huge cost, so this will not be optimal. So that'll be why we want to keep g equal to 0. So no matter how large the cost is, this whole thing is still optimal. So it turns out we can prove that these two are equivalent, and that method is called the Lagrange multiplier method. So here our f is this, g is this, g is actually u transpose u minus 1 equal to 0. So g is 0, so g is this thing. So let me rewrite that. So what we're doing is we're converting that to maximizing UK transpose sigma UK minus a large cost multiplied by this. So now we're just dealing with an unconstrained optimization problem. So we just differentiate with each variable, and then and set it to 0, then we should be able to find the maximum. So the idea is find the place where the derivative is 0. So first we can try differentiating with respect to lambda, which you just get this constant. So you get UK transpose UK minus 1 is 0. So it's basically UK transpose UK is 1. So you'll get this expression back. And the other one, the interesting one, is differentiate this whole thing with respect to UK. So now you need to remember how to differentiate something with a vector. So what you can do is first, the easy way is to find the list of formulas. So you use the formula directly. Another thing you could try is differentiate with respect to each element of this vector and then combine it back. So I'll not do that. I'll just use the formula. So when you differentiate x transpose AX, X is a vector, A is a matrix. with respect to a vector a x, what you get is this is basically like x squared. Differentiate, you'll get the 2 in front and the a and the x. So what you get from this is treating x as uk, a is sigma hat, so you'll get sigma hat 2 times sigma hat uk. And similarly, that's basically, you can treat this as UK transpose identity UK, or you can use another formula just as when you differentiate x transpose x with respect to x, this is like x squared, so you get 2x back. So here, this is just 2 times lambda times x, which is UK, and differentiating with respect to lambda, which is a constant, so you get 0. So this is 0, and this is equal to 0. So if you slightly change this, divide both sides by 2, and rewrite it as sigma hat uk is equal to lambda uk, you can see this is the expression for eigenvalue. So if we can solve for eigenvalues, we'll get lambda and uk at the same time.